Okay, so I want to do an overview of sets, and basically this will be covering quite a lot of stuff quite fast, as there is a lot of it to cover. So it'll be bouncing from one end of the subject to another very quickly. Don't worry too much about getting all in all at once. This is intended really for myself, so I can watch it over and over again. So a set is a collection of objects, and we define a set. Similar if you're a programmer or a mathematician, we define a set by, like we define a variable. So you might have set A. They're very often capital letters, is defined by, and then we have these curly braces, and inside these curly braces we have the elements of the set. So set A is has the elements little a and little b, and let's just sort of look at what properties that has. So the symbols we use, so these curly braces outside there, they help us to define it. We separate it with commas. It's all very, very simple stuff so far. So what can we say about set A? How big is it? Well, it has two elements. So that's actually something we would use. That's the cardinality of A. So we can write, we would write that like this. Cardinality of A, a bit like writing absolute, is 2. What else can we say about A? Well, A has constraints, so we could define A differently, especially if we changed it a little bit. Let's change it to numbers because they're easier to define using constraints. And we're going to use a predicate and constraints at the same time. So we're gonna get all of this stuff in together. So constraints are the rules that are rules that can define a set. So the element x, if element x is one of the set of natural numbers, that's its and it's constrained by 0 is less than or equal to x is less than or equal to 10 times 2x, and then put the curly braces in there. That's not very good. Let me just sort that out. Make this a little bit tidier. Times 2x. Oh, that didn't go very well. It's better. Okay, so what does all this mean? So I could also have written this in a different way, which I'll get to in just a moment. So again, we have the name of the set. So we've defined the set A. We've defined set A. And we're defining it as the things in these curly braces. So anything inside these curly braces is what's defining set A. The elements for now we're going to use x as a variable to represent the elements. This section here is saying that x is of type the set of natural numbers. So x is going to be whole number greater than 0. This section, this bar here, basically says that there are constraints. So there are rules for set up x, and the rules are 0 is less than or equal to x is less than or equal to 10 times 2x. So if we didn't have this bit, then A would be the set of whole numbers between 0 and 10, or sorry, including 0 and 10. So, but we do, so 2x, so A is the even numbers between and including 0 and 10. Now, it may look like that's actually quite a convoluted way of defining it, but what if I change the 10 to 100? Or what if I change the 10 to 50 million, and 0 to minus 50 million, and got rid of the n and put r? So then you see it would become very useful for defining very, very big sets very quickly. So I've covered quite a lot there, so let me just take a step back and talk about predefined sets. So we have some sets in maths that we use commonly. N, shown that we've used here, is one of them. N is a set of natural numbers. So capital N, and it's got this kind of double bar there, is a set of natural numbers. So that's all whole numbers greater than 0, greater than or equal to 0, so it includes 0. Then we have a set, let's make it red, set Z, again with a double bar, and this is all integers, so that's all whole numbers, greater than or lower than, less than 0. Then we have the set R, again with a double bar, and this is all real numbers, so these don't have to be whole numbers. So this is a good point to introduce symbols. There are lots of symbols that we use as operators and just to denote. So we've seen some symbols so far. We've seen very simply the most basic one is the equal sign. So that's how we assign things to a set. We put an equal sign. So we have the name of the set, then equals. We've used the bar. The bar is the constraints bar, so when used in sets, and it tells you the rule after it is of a predicate is what is a property of an element. So it tells you why that element is a part of that set. We have curly braces. I'm not very good at doing curly braces, but these tell you basically where you're defining the set. So anything outside of the curly braces is no longer as part of the definition of the set that you're defining. And you use these a lot in programming as well. So we've seen these symbols so far. Now we're going to look at some different symbols, and these are symbols of how to relate sets together. We were talking before, and I'm going to start with subset, just because we're already talking about three sets that exist already. So we're talking about N and Z and R. And the reason that I want to start with subset is because if you think about it, N is subset means that all of the elements of the first set are in the second set after the symbol, which is this. This is a subset symbol, and this. So all of the elements in N are in subset of Z. So N is all of the whole numbers above 0. All of those are in all of the whole numbers. All of the whole numbers are in the set of all real numbers. So that's subset. The next one I'm going to look at is union. So if the union of A and B is all of the elements of both sets. So if we define A as 1, 2, and B as 3, 4, you can guess AUB equals 1, 2, 3, 4. I don't know what's going on there, but you get the idea. Elements never repeat. So if A was let's just tidy this up. If A was 1, 2, 3, this set would now be the same. So we don't have two threes in the set. So just to make that clear, if A was now this, and the union of those sets would still just be this, because you don't repeat this. Okay. How am I doing? A little bit more symbolism. So what about if I said, so that's union. So if it's that way up, it's union, and that's quite easy to remember because it looks like a U. What about, I'm going to make this a bit smaller so I can write longer sets after it. What about if I said A, B, define A as 1, 2, and just to mix things up, I'm going to define B as A, B. So the next symbol we're going to look at is intersection. So the intersection of A and B is the elements that are in both sets. So the intersection, I don't know if you can guess, of A and B now is an empty set, because there are no elements bar in both. Whereas if I was to add A there, the intersection of A and B would be A, because A is the only element that's in both. So the intersection of A and B is A. Let's move on. So it's intersection, it's just an upside down union sign. I'm going to keep those sets because they're nice and simple. We're going to do subtraction. So A subtracted B, as far as set's concerned, creates a new set, and in this case it's just going to be set A, so it's just going to be 1 and 2. So let's make, again, let's make B include some of the set of A. So let's add in 1, 4 into set B. So what's that going to do to this now? So if it's A subtract B, we create a new set, and it will be just 2, because we ignore everything else and we have to subtract 1 because it's in set B. Okay, so we've done cardinality, section, done predicate. I'm going to take a step back now to a little bit more symbolism. Something you'll come across a lot, which I haven't really gone over yet. So if you have an element A and you want to say it's a member of, you use this. So if A is an element of the set A, little a is an element of set A, then you use that. Whereas if little a is not an element, it's very much like not equals to. And there you go, that's it. If you want to define an empty set, that's very easy. You can either do empty brackets. Just clean up my board a little bit. Never mind. So to define an empty set, you either do this, or you use the Greek letter phi. And it defines an empty set. Useful in some clever programming languages to define an array of an undefined size. So moving on, we've got a few more things to cover and then we're done. Cartesian product. If I write A times B, what I'm actually doing is I'm not multiplying the two sets together. It doesn't really make any sense. But let's define our sets. A equals A, B. Set B is defined as 1, 2. And the way that we do A, Cartesian product of A times B, it becomes, in order, you pair them together. So A1, A2, and the order is important. B1, in brackets, B2 in brackets, and that's it. Ooh. There you go, and that's it. So the order is important, remember that. Power set. A power set is all of the subset, is a set of the subsets, the possible subsets of a set. So let's just make that clearer than mud. So if I want to find the power set of set A, that's going to be easy. That's the power set of A is a new set which includes an empty set. It includes a set A. It includes a set B, the subset B. It includes a subset A, B, and that's all of the subsets. We'd have another curly brace on the end. If I want the complement of A, well, the complement, first of all, let's talk about the universal set. The universal set is all of the elements in the world, in the universe, if you like, in the world that you're working in. So if we're working in, and we're saying that in our problem that we're working in, all of the letters of the alphabet are in the universe that we're existing in at this time. So let's define set. Set universal as A to Z. Then the complement A, C will be everything that's not in A. So it will be C, D to Z for that problem that we're working in. And it doesn't, and if set B is part of the world that we're working in, it will also include 1 and 2. If you think again, if it was an alphanumerical problem and all of the numbers were there as well, it would be a very large set. I mean, we get a super large complement for A. But this is useful when it comes to Venn diagrams. A symmetric difference, a set of elements that appear in A or B, but not A and B. So it's different to subtracting. If you remember, if I subtract B from A, then I get, I take all the elements that are in B and A and I take them away from A. But the symmetric difference are elements that exist in one or the other, but not both. So we can say 3, 2, and that's fine. So the symmetric difference will be a new set A, B, 1, 3, because 2 exists in both. Okay, I think we're finished.